Imagine this: two tiny particles, born together in a cosmic dance, suddenly flung apart. One zips left, the other darts right. Now here's the kicker. No matter how far they travel, whether it's a few feet or light years apart, whatever happens to one instantly impacts the other. It sounds like something out of a sci-fi novel, right? But this is real, and it's called non-locality, a mind-bending concept in quantum physics. Today, we're going to dive into this fascinating phenomenon in a way that's easy to grasp. Let's break it down. In the quantum realm, particles can become entangled. Think of entanglement as a special bond. Their properties, like spin, become intertwined. When you measure one particle, it instantly determines the state of its partner, no matter the distance. It's as if they're cosmic dance partners, perfectly in sync, even when separated by vast stretches of space. Now, this idea made Einstein uneasy. He famously dubbed it spooky action at a distance. Why? Because it seemed to violate a fundamental rule of physics. Nothing can travel faster than light. Einstein believed there had to be hidden variables, secret information explaining how these particles communicated. He couldn't accept that they were somehow connected in a way that defied our everyday understanding of the universe. But here's where it gets interesting. Over the years, experiments have repeatedly disproven Einstein's theory. In the 1960s, physicist John Bell devised a test to put this debate to rest. He demonstrated that if hidden variables were at play, the results of particle measurements would follow specific patterns. Scientists began conducting these tests, and guess what? The results didn't match those patterns. The particles weren't communicating in a way we could explain. They were doing something even stranger. Enter non-locality. The connection between entangled particles isn't about information zipping back and forth between them. Instead, it's as if they're part of a single, unified system, regardless of how far apart they are. Measuring one part of this system instantly affects the entire system. It's a wild idea, but it suggests that the universe is more interconnected than we often realize. So what does this mean for us? It implies that the universe isn't as fragmented and disconnected as it appears. Everything is intertwined at a fundamental level, even if our eyes can't see it. This interconnectedness has some pretty exciting implications for technology. Quantum computers and quantum communication systems are being developed based on this very phenomenon. One of the coolest applications is quantum teleportation. Not the kind you see in Star Trek, but a method for transmitting information instantly across long distances using entanglement. And let's not forget the philosophical questions that arise from non-locality. If particles can influence each other instantaneously across space, what does that say about reality itself? Is the universe truly as divided as it seems? Or is there a deeper, unseen unity at play? At first glance, non-locality feels impossible, challenging our everyday experiences. But the more we study it, the more it encourages us to rethink our view of the universe. The classical notion that objects are independent, interacting only locally, like billiard balls on a table, just doesn't hold up in the quantum world. So, while non-locality might seem spooky at first, it's also incredibly awe-inspiring. It serves as a reminder that the universe operates on principles far more mysterious and beautiful than we can imagine. And maybe, just maybe, it hints at a deeper level of connection that underlies everything we see and experience. Isn't that a thought worth pondering?